Good afternoon, everyone. So my talk is about how to assess the reliability of a deep neural network. So the scenario is as follows. So you have been training a neural network over some data, and then the question is, can you rely on this neural network? So one thing that everybody does is to is to check the generalization of your neural network, meaning that generalization is the capacity, the capability of your network to operate as expected on unseen data, so data that has not been seen during the training. So if generalization is okay, then what is next? Maybe you want to stress a little bit your system. So you will try to see whether it operates as expected on noisy or corrupted data. Just to stress the system a little bit. And maybe it makes sense, because for your application, you are dealing with noisy data. For instance, I am dealing with images. So images are captured with a sensor, and therefore there is a measurement noise. And then these images are compressed, so quantized, and then these images are transmitted to the neural network. So maybe there are some uncertainties, corruptions in the acquisition chain. So if I'm happy with the robustness of my network, what is next? Maybe I would like to see whether it operates as expected on purposely perturbated data. So it's this time it's me that will play the role of the attacker, and really I want to delude my own system and see whether how good it is, how robust it is, how safe it is against the purposely perturbated data. And if I'm happy with the safety, so what is next? So what is next is the formal proof. And then I will have a proof that my system is operating as expected on any data that matters to me. So I will take the example of ImageNet. So the deep neural network is a box over there that succeeds to identify the object depicted in the image. So everybody knows that in 2012 there has been a breakthrough thanks to deep neural network, AlexNet, and there is clearly a before and after AlexNet. So some say that this is the climax of artificial intelligence. So then what would be generalization? Generalization would be I send images and I'm looking whether they are correctly classified. So here my network is able to find that there is a low mower in the picture. Great. The robustness, what it is? Well, I will have noise a little bit and we'll check whether the prediction is still okay, and if it is, I will have some more noise again and again and again until the predictions fail. And this is exactly the turning point here. With a little bit more noise, then the prediction is wrong. So we see that the network, this network, which is the efficient net network, is pretty robust against noise addition. I can do the same with GPay. For instance, I will compress my image again and again and again until the network is no longer seeing a low mower. And this is the turning point again. So it's quite robust against GPay. So what is next? What is next is safety. Then I'm playing the role of an attacker. So I am really looking for the perturbation that delude my system. And here is the result. And we see that the distortion is much smaller. So maybe my network is not so reliable. And then the last step would be certification. I really want to know whether there exists an adversarial example which lies within a given distance. And here is the closest adversarial example that I could find. And we can see that the distortion is much smaller than what was experienced with robustness. So what is certification? Certification can be defined as this. So I have my neural network F. I will define an input domain, which is a region inside the input space. I will define output domain, which is a region into the output space. And then I will define a property. I would like to know whether for any input data inside this input domain, the neural network is taking a result, is valuing a result which is inside this output domain here. And if it does, then we certify this function. So for instance, with my image classification, the input domain will be something like this. I have one image here which is well classified, and then I would like to know whether for all the images which are nearby, meaning that at a distance lower than epsilon, whether all these images are classified as a panda. So this will be my definition of the input domain. And for the output domain, it's just all the predicted probabilities such that the class panda receive the maximum probabilities. So the goal of the certifier is to say whether this property, which is defined by a given network, the input domain and the output domain, is correct or not correct. Does this property holds or not? So the certifier can make two kind of mistakes. It can make false positive, meaning that the event the certifier will certify this property whether the property does not hold, and there are also false negative, meaning that the event is not, the certifier is not certifying, whereas the property does hold. Some people speak about soundness, meaning that there is no wrong certification, so if the property holds, then the certifier if the property does not hold, then the certifier will never certify. And completeness means if the property holds, then the certifier always certifies. And then there is basically two approaches. One approach is the forward approach, where we try to see what is how this hypercube here is mapped into the output space. So we are looking for the image of this blue hypercube, and we will see here that the image is not strictly included inside the output domain. Therefore, it means that somewhere in this hypercube, there are images which are not classified as panda. So the property does not hold. But I can do the converse. I can try to see whether this output domain is mapped back into the image space. And for instance, here in a range, we have all the region of all the images classified as panda. And we see that my blue hypercube here is not included inside this set. Therefore, there are images, and they are here. There are images that are not classified as panda. So, forward approach. Formal proofs belong to this approach, and we will consider a neural network. That a neural network is just a series of transformation, a linear transformation followed by a nonlinear transformation, followed by a linear transformation, and so on and so forth. And then for each step, we will see how the hypercube is mapped into another domain. So with a linear transformation, it means that my hypercube will be rotated and stretches along some directions. And then the nonlinearity will truncate the corners here that are in a negative space. Because the nonlinearity that I considered here is just the ReLU function, the ReLU activation function, where any neurons that takes a negative value will be reset to 0. So this explains why there is a truncation here, because that value here will be negative, so the ReLU function will reset it to 0. And the same for that. And then I apply the second linear transformation, which amounts to have a rotation and scaling along some direction, and then I will truncate again and again and again. And it happens that I was starting with an RPQ here with 1, 2, 3, 4 faces, and now I have a polyhedron with 1, 2, 3, 4, 5, 6, 7, 8 faces. So there is really an explosion of the number of faces, and therefore it's not tractable to manage the description of such a complex polyhedron. And this happens because any time that a neuron can be active or inactive, then it means that I have a new facets. And therefore, this problem is indeed NP-complete. So what people do is that they are doing some relaxation. For instance, they will try to consider to manage a simpler polyhedron, like hyperrectangles, and then they will try to consider to find what is the smallest hyperrectangles that contains these blue blocks here. But therefore, the certifier is no longer complete, because at the end I will have a region which is bigger than the image of my blue hypercube. So it amounts to have some false negative. It amounts to not certifying something that I should certify. So here are some papers about formal proofs. So the very first one was real X, which is a sound and complete, but not really scalable. You can only apply this certifier on very small neural network. And these are papers about relaxations, different relaxation that allows you to apply these certifiers on even convolutional neural network. You are more scalable, but then you are not complete. You are sound, but not complete. What about the Blackboard approach? In the Blackboard approach, it's typically the safety assessment. So I will play the role of an attacker, and I will try to find what is the nearest adversarial example. So basically, I will apply a well-known attack like a Wagner, like PGD, like BP, like whatever, which are all more or less are making a gradient descent to find an adversarial example. The problem is that these attacks do not come with any guarantee. So they find adversarial examples, but it's not clear whether this is the nearest adversarial example or not. Therefore, those techniques are not sound. They are complete, but not sound. Another idea is relaxation. So it's trying to finding the map back of the output domain. And in this paper, for instance, with FastLane, they are able to find hyperplanes that are just below and above the frontier, locally around a given point. So here, for instance, we will find that there exist images not classified as panda, because the lower bound cuts the blue compute. So this technique is sound, but not complete. And then our approach. So our approach is very different. We apply some method from the statistical reliability engineering domain, and we consider, indeed, we first consider a statistical distribution of the input. So basically, we say that the input is distributed uniformly over the input domain. So which is quite strange, because for the moment there was no statistical distribution involved. And then we will define the probability of failure. So it's the probability that the output of the network doesn't belong to the output domain when X is distributed like that. And then we will try to gauge, try to measure this probability of failure. And we will say that if this probability is bigger than a given level, then we will not certify. So there is clearly some adversarial examples inside the blue hypercon, the blue hypercube. And if the probability of failure is lower than a given level, then we will certify. So therefore we are complete but not sound, because for instance, if the probability of failure is below the critical level, but not equal to 0, then we will certify something that we should not. But so it's a kind of a relaxation of the certification problem with hypothesis testing. But the issue is now, how can I estimate a very small probability? Because of course, if this critical level here, PC, goes to 0, then my schemes amount to a real certification. So I would like to have a level, PC, which is extremely small. Therefore, I must be able to estimate the probability of failure and to compare it with this critical level. So there was a very first paper, Prodero, which was using Monte Carlo simulation. But the problem with Monte Carlo simulation is that its efficiency is very, very bad. Meaning that if I want to know whether the probability of failure is around 10 to the minus 9, then I must generate billions of inputs. And indeed, there are tools which are much more featured than that. They belong to the rare event simulation domain in statistics. Tools like importance sampling, importance splitting, or this particular algorithm that we use called last particle. So this algorithm is an iterative process managing very few samples, and iteratively they will try to craft samples that violate the properties. And basically, the number of cores, so the complexity can be measured at the number of cores to the neural network, and this number of cores is proportional to the log of 1 over PC. So there's a log here contrary to the Monte Carlo simulation, and this is really the game changer. More than that, we have, so this method is complete, but it's not sound, but we can control the soundness. So basically, the probability to have a false positive will be lower than alpha, something that we can set, that the user can set, and can control, and of course, the lower alpha, the bigger the complexity. So I don't have any time to explain you how the last particle algorithm is working, but we apply it on the Akasix-U scenario. So basically, you are in this plane, and you change your direction because another plane is coming in front of you. And depending on the speed, on the angles, on the altitudes of the airplanes, you should take a decision. And the decision will be taken by the neural network. So you should really be sure that you can rely on this thing. So here are, for instance, runtimes where we compare with ERAN. ERAN is a sound and complete method. So you can apply it because the neural network is very small. And we can see that our method is much faster than ERAN. However, our method makes some false positive here. So for instance, we have been certifying the neural network into a situation where we should not have done that. But what you should know about formal proof is that an SMT solver like ERAN takes 4 decisions, indeed. Maybe it will certify your property, maybe it will not certify your property, but sometimes it just give up, saying no, the problem is too complex. And sometimes you will try to solve the problem, and it takes too long, and then you finally stop it. So you can see that we have been able to do that just on a laptop. So, and with a critical level which is 10 to the minus 50. So it's a super small probability, critical probability. Another example is we apply our scheme on the ImageNet, and then we cannot compare with formal proof certifier because they cannot scale up to convolutional neural network that tackle images from ImageNet. So this time we will play around with NVIDIA V100 GPU. The critical level is 10 to the minus 15, and basically it takes 26 to make a decision among the nets, which is kind of small convolution neural network, and it takes 30 seconds to run on resonance 15. And you can see here the average number of calls. It takes so long because we have to query the neural network 1,400 times. And we can see also that as epsilon, which is the size of the hypercube, is growing, then it takes less time because the probability of failure is bigger, so it's easier to estimate a bigger probability. And of course, we are certifying less images. So our proposal is just applying statistical probability engineering to a very good simulation to this certification problem, such that we can scale better and can be faster. We control the false positives, so the lack of soundness with a given parameter alpha. And we can apply this on distribution like this, so a uniform distribution over the input domain, but we can also generalize to Gaussian distribution or whatever. Moreover, we can also apply this on the uniform distribution over a sphere, where formal proof are not able to do that. And indeed, we are using the neural network as a black box. I mean, we are not taking advantage of the fact that we know that this is a deep neural network. So this can be applied to deep neural network. There's nothing specific to them. It can also be applied to SVM, random forest, nearest neighbor classifier, regressors, whatever you want, under some mild conditions. And so everything is explained in this paper that was accepted to NeurIPS this year. Thank you very much.
Thank you. Thank you, Teddy, for the presentation. It was very interesting indeed. We have time for a couple of questions. Who starts?
I'll start. Thank you very much. So I liked very much the figures that you showed in this presentation. I have one question regarding the safe part of the talk. So you applied your approach on the Akasu use case or Akasu applicable data. So where is the safety side in this application? And did you?
The safety side of it.
Yes. And did you try other applications, like for instance, in autonomous driving, where you have safe constraints, etc.?
No, we're just applying on AK6U. So we're basically, you want a neural network to pilot a plane. So this safety issue is quite crucial.
And the dimension of your data is small, right?
So sorry, I don't hear you.
The dimension of the inputs.
The dimension is very small because here you have your location, the location of the hoverplane, the speed and the angle and the altitude. So it's very few parameters. So it's on tens of parameters. Whereas for images we have hundreds of thousands pixel values.
Yes.
So this is the reason why we can compare to formal proof.
Okay, I understand.
To see that we are making mistakes sometimes, we are making false positives sometimes, but we never give up and we never time out. The formal proof. And the goal is indeed to scale in order to have some reliability assessments for really large deep neural network, such as convolutional neural network.
Okay, I understand. Thank you very much for that question.
I have another question.
Thank you. When you were presenting the result for the AKS problem, you showed that you had a value of alpha C about 10 to the minus 50, something like that. But when you compare it to Iran, you have like 10% of false positive, and in the previous slides you had something like the probability of false positive should be less than alpha C. So I don't really, isn't that kind of worrying, or maybe I misunderstood something?
Yeah. So it's the false positive of that test over there. The false positive of this hypothesis test. So basically there is a false positive here if the probability is bigger than the critical level, and yet I will claim the other way around. And so whenever, and this can happen if P is really close to PC. I will have a very hard time to know whether P is lower or bigger than PC. So there will be some false positive, but at a lower level than alpha. But this is the false positive of the hypothesis test. So there is a confusion here. And here, for instance, we have tested again and again plenty of times those 9 cases, and it happens that we always certify. So it's really the case where the probability of failure is lower than PC, but not equal to 0. So maybe you will take the risk, say, okay, 10 to minus 50 is never happens. So a bad event can never happen, and you will take the risk. Because yes, there is a valuation of the property, but it's the volume is so small, so the probability that it happens is so small that you will take the risk.
Okay, thank you. Is there any other question or remark? Jalal, also you can answer questions if you want.
How does it behave in case of the output space is not convex or not simply connected, which is typically the case?
But we have to resort to is a scoring function. For any input, I should have a scoring function which tells me whether I'm about to violate the property or not. So this scoring function should be a real function, give me a real value. So basically, for instance, if it is positive, then it means that I will be well classified. If it is negative, it means that I will be not well classified, because the classification will be wrong. So therefore, the last particle algorithm is driving the input data towards the events, which is the valuation of the property. Thanks to this scoring function, which tells, well, you should go in that direction because probability, the adversarial examples are over there. But for we don't care whether the map back of the output domain is convex or not, is convex or not. We don't care, provided we have this scoring function.
Thank you.
Okay, thank you. I think we have to move to the next presentation. So Stéphane Canet from INSA Moi.
Okay, thank you. Thank you for inviting me. And thank you, Teddy, for the presentation. I'm going to continue your presentation, but in a different perspective, one you introduce, verification. So it's a joint work with the team. Remo is artificial intelligence chair we have in Rouen, in INSA Rouen, with all the guys working in the team. So some nice picture to begin with, because we are talking about attacks. So we are a bit tired, it's the afternoon, so we need a nice picture. So the picture illustrates what is an attack. So you receive mails with attack on text. You just change A, commercial A, and this is just to fool your spam detector. But you can also attack face detection identification system by wearing stupid glasses. Or you can try to attack person detection system by wearing this patch here. And then the system fails at recognizing this person as a person. So, but you can also attack, you mentioned vehicles. So you can attack autonomous vehicles by modifying, making little perturbation in the road signs. By painting your car with special paint, and the system will recognize, will classify your car as a cake. This is and an experiment has been made also to fool your Tesla. Was the owner of the Tesla. So you take these three, and yet you just add a noise here, like Pinocchio, and the system recognizes 85. This is problematic for the Tesla. However, it was the old system, and some attacks has been made also by just projecting false images in front of the car, and it was the Mobileye system which has been fooled by this system, the Mobileye installed in the Renault Capture, I think. Nice picture. So we are going I'm going to explain how to find an adversarial example. So if I take Teddy's talk, is exact method, formal method to prove the existence of an adversarial example. So yeah, since I will enter a little bit more into the detail, I introduce some notations. So I have a neural network that takes X as an input, and it provides an output. So here the legal output is 1, and A is an attack or adversarial example, and then it's just the same as X, it's not far from X, it's a perturbation on X, and the neural net will classify this A as a 4. So you have attacked the system because you just modify some little pixel on the input image, and the output has changed. So to define the adversarial example, you need 3 components. Teddy mentioned that. Of course, you need to find a validate example A, and this valid example has to be close to the point where you want to design your attack, so you have to define the distance. So Teddy told us about the infinite ball around the point, but you can have L2 ball or whatever, any kind of ball. This is the distance or the similarity measure on the input. Also, you can define a loss, adversarial loss, to measure the distance, the way you want to assess the fact that you have attacked your system, your attack is a success. So of course, when you're dealing with classification, there is a very simple thing. If the predicted class is different from the one you want, then you declare that the system has been attacked. So in this case, the loss is just the difference between the output. Okay, so Teddy mentioned a lot of approximation. I call them heuristics, and he mentioned about the Carlini-Wagner attacks or PGD attacks. So depending on the ball you're dealing with, that is the distance on the input, some are more popular than others. So the most popular, if you're interested in L infinite ball, is the PGD. And if when dealing with the L2 norm, this is Carlini-Wagner or CW attack, it's the way of finding an attack. So together with these heuristics, you have popular software such as Cleverance or art software that help you to find, to make this system works. But here you find an attack, but you're not sure that it is the best attack, as Teddy says. So the way to find adversarial example, Teddy focused on this third way. The robustness as a verification problem proposed by Katz and all. But it turns out that there exist other ways to see this problem. And the first one is to minimize the adversarial distortion. So the idea is to minimize the distance with the constraint that The loss also, it's in some sense, it allows different view. For instance, here, we can play with infinite norm, but we can play also with L2 norm. With infinite norm, we have a linear cost. With L2 norm, we have a quadratic problem. But they are very hard optimization problems, as we'll see. And we focus on this formulation. So we can have a different formulation with different guarantee. If you minimize the loss imposing, it's a dual view. You minimize the loss, and you say you want to see if you find an adversarial example within a certain goal, depending on the way you define that. Is the point of view of Wong and Kotler, for instance, presented in ICML in 280. So we are interested in this first formulation, minimizing a distance with a different output. So I have to precise to resay what Telly mentioned it. If you have a neural network, this neural network has a linear combination here, the linear weights W and the linear weights V, but also we have this real U, which is nonlinear and non-convex. So the function f can be modeled as zeta is the real U of Wx plus beta, x being the input, and then the output f of x is V zeta plus gamma. And here, what is zeta, the real U, is the maximum between h and 0. So you can take this definition of the function and rephrase your optimization problem. But if I look at that, I have two nice things. This is a linear combination, so it's a linear constraint. This is linear also. So the ugly thing here is the maximum between 0 and 1 because it's non-linear, non-convex. It's piecewise linear. So a way to deal with this piecewise linearity, it's a so-called reduplex. So Teddy mentioned it also, but I just enter a little bit into detail to show you how it works. If you want to model this zeta maximum function, so you want to model this function, which is 0 there and linear on that part. So the way to do it in optimization is to associate to each of these ReLU functions a binary variable. And you have a binary variable, b, and you say, okay, if b equals to 0, that means I'm here. And if b equals 1, that means I'm there. And so, when you have that constraint, say zeta is maximum of h, you say, okay, I will just rewrite this constraint as 4 linear constraints. So since they are linear, this is very nice. However, to write this linear constraint, I have to introduce this b here, and the b is modeling the two cases, because I'm piecewise. Ever, if b equals 0, I'm here. Look, if b equals 0, zeta has to be greater than 0 and smaller than 0, that is equal to 0. And if b equals 1, I am there, because b has, zeta has to be smaller than h, and since it's equal to 1, this thing will finish, and smaller and greater than h, it has to be equal to h. So depending on the value of b, I have zeta equals 0 or zeta equals h, modeling this function. So I can rewrite, take that and plug it into the optimization problem, and I find this problem. This is the initial problem. I want to find the adversarial example close to x, so I want to minimize the distance between x and I, with the constraint that the output is not the desired output. So it's an adversarial example, I change the output. Okay, but what S is the output? So it's the V zeta, and zeta is the maximum. Here is the pain, because this is non-linear. You minimize here, depending on P infinite, it's linear, P equal 2, it's quadratic, P equal 1 is linear also, piecewise linear cost function. Here you have linear constraints, but here you have maximum. Actually here also, it's another difficulty, but not so much, so important. So you reformulate that with your 4 constraint by introducing here b variable as much as this ReLU activation function. So you're happy because you have linearized your system. It's a linear program. But you are not happy because it's not a very nice linear program, because it's a linear program, but with continuous and discrete variables. So it's called a mixed integer programming. It's a linear program with both variables, continuous and discrete variables. And this is very hard, as Teddy says. Of course, this is a NP-hard problem. And you have the optimization issues, and you have to find the B. And to find the B, you have a combinatorial issues. So you have not only optimization, but combinatorial issues. You have to handle both problems. So I'm getting old now, and when I was studying, we have seen this kind of problem in the 80s, and my professor at that time says, okay, this is really intractable. If you see such a problem, don't even look at it. You will never be able to solve it. But if you go through simple computation with the progress in the understanding of the progress of computers, the problem of software, the progress is on solver, you figure out that now the computer we have, the way of dealing with this problem makes them tractable in some sense. I'm trying to see how we can see this problem and try to solve them. But we have to pay attention and try to reformulate and to help the solvers to find good solutions. So how does it work to solve such a problem? To solve such a problem, because they are binary, so the idea is to find two kinds of bounds, lower bounds and upper bounds to the problem. So the lower bound first, it's a very simple relaxation. You say, okay, I want continuous, I want discrete variable, I don't know them. So I made a relaxation, I say, oh, instead of discrete, I take continuous variable. So of course, this is not the solution of my problem, but when I find a cost, it's a lower bound of my problem. I know the solution is not smaller than that. And then I'm going to make some choice of some B. So maybe this B is 0 or 1. I'm going to choose which is the best one. And then I'll try with these choices to increase my lower bound. And on the other side, I will fix some B, choose some B, 0 and 1. And then I optimize, I solve this problem with fix B in A. And then, because my B, maybe they are not optimal, but I have an upper bound here with fix B. And here again, I will try to change some B from 1 to 0 and 0 to 1 to put this upper bound down. And this is the game of the optimization. You start with lower bound, upper bound, and you go through the tree of all possible B's, and then you are going to try to make them go together, because when the upper bound is equal to the lower bound, that means you have found the solution of your problem. You are the right. So, what's happened when you try to solve this problem? Sometimes it's easy to find an optimal solution. For instance, here, very easy in this problem, you find the optimal solution because the upper bound is okay. But it takes a long time to prove it's optimal because the lower bound has to go through all possible combination of B to really prove that this is the very best one. That means that when the solver is well tuned and well helped, you can find a nice solution very quickly, but it takes a long time to prove that the solution is optimal. So, also, you can play on some factors to improve the quality of the solution. You can try to play on the initialization. Of course, if you have a good idea on the solution, you start close to the solution, you go faster towards it. So initialization is a very important issue. Also, you have to think about relevant relaxation, and sometimes you add some constraint and relaxation that helps you to accelerate, and to think about the clever combinatorial exploitation of the different solutions. So we know that very often the adversarial example is very close to the example, so the number of activation that has changed from the beginning is very small. So if you start with the B of the initial example, the number of changes on your B is small, and so you can accelerate and you can exploit the solution. So this is the way we are working. We are trying to see how to improve this MIP solver to solve bigger and bigger problems. So, okay. So I just give you some empirical evidence, some experiments we have made. So we work on CFAR. So it's smaller than ImageNet, but it's bigger than the air collision system. There are still images with a little three-layer, multi-layer perceptron, just with a regular machine, not too big, but not too small. So we find 88 exact solution. So we put a Tmax of 15 minutes. So within 15 minutes, in 98% of the solution, we find an adversarial example, which is, we prove it is the very best solution of the problem. And the computing time, the mean computing time on this one example, we use a solver called Cplex, which gives the best results, is less than 6 seconds in average for each example to find the proof that we have a guarantee. So as an example, if you find an approximation, you run Carlinier-Wagner, it's much more faster, but you just have an approximation. Here we have a proof, exact solution of the problem. And one thing we thought was interesting, so we made the computation for the L2 norm. So in average, we improve the solution of the Carlini-Wagner by 20%, which is something on this small example. Okay, so I just finished the presentation saying, okay, we are still working on this myth, trying to improve it, and trying to find a good and nice relaxation to have a more efficient system capable of dealing with a larger image and so on, to work on ImageNet with such an approach. Thank you.
Okay, thank you. Interesting. We do have time for questions. Please.
Hi, thank you, Nathan. On slide 13, about you said it's easy to find a solution, but it's difficult to prove that this is to prove that it's actually. Wouldn't you be better off with like maybe a certificate which is like true a certain probability, and then this would so for example you would, instead of going through all the B's, you would try to solve some B's. I'm just like thinking out loud, and then this is going to be okay with a certain probability that you can confirm.
Okay, so we work on that. A student that not exactly randomly generates the B, but he made a smart search using PGD to improve the search of the B's and then solving the linear problem for each. And it has good result with this method, but it's not exact proof. But he discovered also that the number of changes in D is reduced. So it's a reason why theoretically the combination may be ugly, but practically it's not so ugly. So if you're clever in the way you explore the variation of the B's, the activation that changes, it's very interesting. So it's very important, it's the key issue, the way the B's are changing, how to monitor them, how to find them.
Sorry, I may have missed an information or maybe it was not covered. So I wanted to ask regarding the difference between having an adversarial attack on an image or on certain data, or like a fault being happened because of noise or something like that. Is your system able to differentiate between the two different scenarios, or just you're considering everything as an adversarial example?
Yes, we focus on adversarial, on attacks, because we want really to minimize the distance, really to find the closest example with this constraint that fool the system. If you think about the robustness, as Teddy introduced, you have to think an average with some noise. And I've seen in some presentations the difference between Shannon and Amin. So Shannon is considered robustness as average or something. Here we are talking about someone who wants to attack you. So it's specific design noise to make perturbation. So it's different.
Okay.
And here in the presentation we are really dealing with this specific noise attacking the system.
So maybe it has its own pattern which is different from any kind of
Yeah, it's a specific noise designed to fool you.
Thank you.
It's like a magic tour.
It will be the last question.
Yes, thank you, Stefan, for the presentation. So just its remark. So there has been recently a very nice library introduced by and worked by German people called Robust Branch Library. So we are in the robustness workshop. And there you can find a new attack called auto-PGD. So it is an automatic PGD attack. And it is much more efficient than PGD. So the paper, I think, was in ECML very recently. And now it is becoming the state of the art to check robustness and etc. So just
Okay, it's a work by Matthias Heinz.
Yes, exactly.
And
Yes, this
Pointwise,
thing.
I'm
Yes.
following them. They are very clever and very tough.
yeah, and the paper is very highly cited now.
Okay. Thank you. Thank you very much.
I think we are moving to the next presentation. It will be Jalal Fadili from NCCAN. Stefan, can you manage the...
Okay, so thanks very much for the invitation, and I'm very happy to be remote
Not
with you.
here.
So I'm going to take you in a journey in robust learning using robust optimization. So typically this will be a joint work that we've done with Frédéric and also a joint student of us, Mediapla. Okay, so when Frédéric asked me to give this talk, actually I wanted to give first an overview of what robust optimization has to do with the adversarial domain, let's say. So we've seen different point of views or some differences and common points between presentations of Stefan and Tini. And I think that what I'm going to present here is going to be a sort of a complement to what they have been presenting. So I'm going to be in the classical supervised learning setting where I'm going to take a metric space, typically it could be even a polished space, which is the data space, Z, and with a metric D. And the Z, you can think of it as the product space of the input and the output space, X and Y. And I'm going to equip this space with a probability measure, and theta would be my parametric space. And on this, I'm going to define a loss function, which is basically a lower bound. It could be positive, it's not a big deal. And it's going to be a measurable function in Z with respect to the measure rho 0. And the goal is to solve this minimization problem that you're seeing here, minimum over theta, which is always parameter space of some risk, which is the expectation over the measure rho 0 of my loss. Okay, so when I do this, basically what I want as a desired property is that to be at least have some type of robustness to perturbations in the data generative distribution rho 0. And it turns out that, as you all know, that neural networks are vulnerable to those perturbations, adversarial examples, where imperceptible perturbations to data may be quite misbehavior of the model. And you've seen very nice pictures in the talk of Stefan, for instance. In fact, many adversarial examples on defenses that have been proposed, but the problem is that many of these defenses were either broken or are computationally intractable in practice, or at least lack some, let's say, guarantee. So in fact, it is even challenging to identify classes of attacks against which one can defend, or even if they exist. So you've seen the talk, for instance, of Stefan, where basically he has shown that typically this problem can be seen as any hard problem in general, for instance, through the lens of formal verification. And we know that recently sorry. Okay. And recently we have seen some complex organizations of this that have started to emerge. However, the problem is that they do not scale with large networks. So, is this story over? In fact, the full implications and mechanisms for the emergence of adversarial examples are not completely understood, and still a very active research area, and probably there are many mathematical reasons which are involved there, and people are still trying to understand what's going on there. So we have some explanations that have emerged for typically that this may be a consequence of the structure of deep networks their ultimate linear structure. And there is also explanation saying that non-robust features in the data are actually responsible for adversarial or for the lack of robustness. So typically these features are could be highly predictive but brutal. And in fact, there is also a lot of lines of research that say that even, in fact, in classification, adversarial examples are even unavoidable for certain high-dimensional settings. And there are 2 points of view to explain this. The first one is through the lens of the constraint to measure phenomenon in high dimension, and more precisely using tools from isoperimetric inequalities. And basically what it says is that if your data is sampled from a concentrated metric, probability measure, space, could be the sphere, the hypercube, for instance, then any point will be susceptible to high adversarial risk, meaning that that point would be either misclassified or could be attacked. And this, in fact, finds its foundations in the fact that for data which is supported in such spaces, what we call epsilon expansions, because basically we want to see what are the consequences of the perturbations. And if you have a perturbation of, let's say, some epsilon and epsilon super positive, then you are inflating your regions by an amount of epsilon, and this can blow up even for a small epsilon. The other point of view is that of interpolation. So in fact, if you take your, let's say, classification problem as an interpolation problem through an interpolating classifier, and if you have some noise on the data, but also in the label, then adversarial examples can become also unavoidable. And what we can say is also is that the set where predictions may differ from the ultimate classification. This set is a dense subset of zero volume. So it is a dense subset, however, it occupies a zero volume as the number of data sets goes to infinity, which leaves some form of hope. So anyway, the existence and the pervasiveness of adversarial examples, they all point to the limitations of the standard IID model. So what can we do? So the idea is basically to quantify the impact of the adversary by perturbing the data during the training. This is something that you've seen also in the talk last time. So here, for instance, I'm presenting a very simple example where with the 2 moons, and here this would be basically the standard training, and you see that near the edges or near the decision region, if you perturb a little bit here or here, then you're going to switch basically the label of your points either here or here, and even here. So basically, if you want to train your data, maybe you can train some accuracy for robustness, in which case you may end up with some decision region, which is right here. And here, basically, you are having errors, for sure. However, you're going to gain in terms of robustness. And this is basically the idea of perturbing the data during the training, doing some adversarial training. So we have several notions of adversarial training. The first one, and so here I'm going to focus on 2 of them, which are based on robust optimization. The first one is what we call the Pointwise perturbation optimization. So typically I'm going to define here another risk, which is the one presented here. I'm not going to take the expectation with respect to so I'm going to take the expectation with respect to row 0, but now I'm going to perturb around all points which are in the support of the distribution in row 0. So this is where I'm modifying my risk, typically, is that I'm taking here now another loss, which is minimum of all the losses in some ball around the epsilon metric peak. So this is something that we've seen more or less in perturbation by Stefan. On the other hand, we have what we call distributional perturbation optimization, so DRO. And in this case, what we're going to do is that we're not going to perturb the data pointwise, we're going to perturb the distribution of the data. So now I'm going to optimize not the risk that I had before, but I'm going to optimize the worst case risk that I had in some ball around row 0 in the metric D, on the probability space P, which is supported on zero. So this is the second risk we're going to try to do. So basically, this is the holy grail. We want basically to allow the perturbation of the distribution and to optimize, to minimize in the primary theta the new risk, which is the perturbation of the original risk over the ball or around rho zero of a radius epsilon. However, the richness and the choice of D will affect both the richness of the uncertainty set, but also the tractability of the resulting optimization problem. The main difference between these two problems is that even if Z here is finite dimensional, this problem is completely infinite dimensional. Okay, unless you're taking all the atomic measures with finite number of atoms, which doesn't make sense all the time. Some approaches have been used in finite dimensional parameterizations, typically constraints on the moment, the support or directional deviations as a proxy of this problem. Other were using non-parametric distances, divergences, for instance, between probability measures. But as you certainly know, divergences are not very stable, for instance, to singular supports. And this is why people have been moving to the Wasserstein distance, the optimal transport distance, which has become very successful in this context. And one of the main motivations is that unlike the other distances and divergences, the Wasserstein ball around rho zero includes distributions with different supports. Supports are different from rho zero. And typically, it will allow to learn from and see data. Okay, so basically, when you have these two problems, there are many challenges. They are both algorithmic and on the learning level. So I'm presenting here on the left the DRO problem, and on the right, the pointwise version of it. So the right-hand side, we can do things about it, at least from the algorithmic point of view. The left-hand side is a little bit more complicated. It's even much more complicated because of the infinite structure of the optimization problem. So the natural question is, can we relate these two problems? And in fact, the answer can be true under certain circumstances. So for a limited class of convex losses and costs, we can convert the DRO to some sort of regularized empirical risk minimization problem. And for a larger class of smooth losses and costs, we can convert, again, DRO to a Lagrangian form of the pointwise or the robust optimization formulation. So I'm going to come back a little in a while to this in a little while. Okay. So, in fact, even the PRO is very challenging to minimize. In fact, except for very specific cases, the inner non-concave problem is very intractable. And it is even really hard, for instance, if you look at the problem involving non-smooth non-narrows with railroad activations, for instance. The proposal we have made with William and Frederic is that, in fact, we can approximate PRO with PRO with some provable surrogates and design probability conversion algorithms. And the idea is to use some smoothing. So let's get back here. So typically, what has been done in the literature is the following, let's say, relations between DRO and PRO. For instance, if you assume that L is continuous, then you have even this equality here between DRO and the Lagrangian form of the PRO. So we have equality, but now you have to optimize over this primary gamma, which is not easy at all. And the supreme problem is still very intractable. In other words, people have been presenting under other, for instance, if rho zero is totally measured, if L is elliptics, then you can have this PRO relaxation of DRO, and you have really uniform approximation in N, which allow to appeal to gamma convergence arguments, which is independent of epsilon. However, we only have empirical risk, and the problem is that the PRO problem is not separable in the N variables. And the superior problem is still, the inner problem is still very intractable. What we have come up with is that we can approximate indeed up to accuracy epsilon of the DRO with PRO in the case where the loss is Lipschitz continuous, uniformly theta. And in this case, we have uniform approximation. However, indeed, it is dependent on epsilon, but anyway, we're not going to allow epsilon to be very large, so this is okay. And we're going to tackle the inner problem by using some smoothing. So for instance, now the PRO, I'm going to change it to this guy. So people who are familiar with optimization and machine learning, they may have recognized here that we have replaced the PRO with the supremum or the max there, we have replaced it with some sort of a log sum x, where now the sum is just an iteration. So we're just replacing optimization with an iteration. Okay, and what we can prove is that the DRO can be approximated, well approximated with the smoothed PRO with precision that is controlled with tau and epsilon and goes to 0 as epsilon goes to 0 and tau goes to 0. And when we can even relax SPRO by replacing the iteration with sums, which we can implement in this case. And in this case, we can also control the difference between the two objectives, where now the rate will depend also on the number of points that we sample, but it doesn't depend on the dimensions exponentially. Okay, we have also control on the gradient. So if you compute the gradient of your guy here, when you replace the integral with a sum, then you can prove that with high probability, or even almost surely, if t is strictly positive, that the gradient you're going to compute will approximate what we call the clock differential of the PRO. Because this, even if L is differentiable, the sup of L is not differentiable. And you can prove that, in fact, you are in a ball around your clock subdifferential. And the radius of the ball is controlled with tau and n. And in fact, this gives you an algorithm through sampling that not only will give you the worst case adversaries, but also a good estimate of the subgradient for HGD. So for instance, if you look at HGD, you're going to apply your HGD in this case by taking the directions which are dictated by the smoothed version of the smoothed PRO. And what you can prove is that you have convergence, in this case, of your iterates theta k. So they're going to converge around, let's say, the critical points. But if you allow the temperature and the number of samples, the temperature to go to 0 and the number of samples to go to infinity with the number of iterations, then basically you're going to get even a critical point of your original problem PRO, which itself approximates well the DRO problem. Okay, we have many other guarantees, including generalization bounds in the parameterized regime. Of course, we don't have anything so far in the over-parameterized one. But no, we are still working on that. Anyway, just coming here to the summary of my talk. Okay, the full applications again and mechanisms of the emergence of adversaries are not completely well understood. I believe that it seems possible that several mathematical effects combine to produce adversarial examples, not a single one, and this still necessitates a lot of work. And in fact, the common point of view of people working in this is that the existence and pervasiveness of the adversarial examples points to the limitations of the standard IID model. Hence, the robust optimization lens, which offers a principled way to get probability guarantees, both in the computational algorithmic side and the statistical side. There is much to do in this area. So typically, what happens in the non-smooth case, for instance, if you're using Borrelio in your neural networks, so this is completely open. Well, what about the fundamental limits, which are completely independent from the algorithm? Can we say anything about the fact how the adversarial training compared to the optimal training or even to the standard training as a function of epsilon? There are some preliminary works on this. And also, as I showed you before, basically when you try to make your learning robust, you're going to trade some accuracy. And in fact, this smoothing effect of robust optimization really still needs to be well understood. And finally, the guarantees that we see most of the time are guarantees in the under-parameterized regime, which is the standard generalization regime. What happens in the over-parameterized regime, where basically deep neural networks or even wide neural networks operate, which global minima, for instance, are selected by the robust training algorithm. And understanding, for instance, the implicit aggregation and the inductive bias of, for instance, HGD in the adversarial setting is completely open. Okay, with this, I'm done, and thanks very much for listening.
Thank you very much. So I think we can take one question.
Just one stupid maybe question.
That's not a stupid question.
So here you applied the transformation log of exponential. Have you other ideas to, for instance, to replace the log with another function and the exponential with another function? Like, for instance, taking an increasing function in the place of. So why log and exponential?
Because the proxy for this
I don't hear you very well, sorry.
Okay. So my question is.
Can you try this one?
My question is, so you apply the transformation log and exponential. Are there any other choices?
Actually, this comes from a regularization of this problem. So if you take the left-hand side, PRO, you can write this as a supremum of over probability measures, which are supported in the ball of radius epsilon. And then you regularize this with the Kullback-Leibler divergence over absolutely continuous measures, which are dominated by the uniform measure. And this gives you the log.
Okay, so this comes
it has
from.
an interpretation.
Okay, it comes from the
And
KL.
actually, the log sum x comes exactly from this.
From the KL. Okay, thank you.
Okay, so thank you again, Jalal.
Thank you.
So we're moving to the next presentation, and we have
Okay, thanks for the invitation, for the nice talks that we've listened to this far. So the stage has been set like perfect. The stage has been set like perfectly for my presentation. So I'm going to floss over some of the introductory stuff I prepared, not knowing what will be the audience for this presentation. So I'll be the pessimistic person. I'm going to present negative results on robustness. So like limits to what you can do. So it doesn't matter how much regularization or this kind of stuff you do. There are certain limits which are just fundamental. So okay, yeah, the compulsory photo about a cat going through a neural network. It gives a cat, if it's well trained, if you add some noise, or well-crafted specific noise, so you can make it say something as an ostrich, for example. And the whole point is that this perturbation is very small. And this have real consequences in real life. You could derail real-life AI systems, for example, for doing things like face recognition or even more critical stuff. So, as we've seen some hints in the previous talk, adversarial examples require rethinking of the whole empirical risk minimization part, which is dominant in ML, and also to rethink what it means to generalize, what it means to predict well on test set. Okay, so there are many types of attacks. Most of the attacks you have seen up to this point are so-called test time attacks. So the model is trained, deployed, and then at test time, attackers could modify the input to have the model output or something else. There are poisoning attacks where you could actually inject malicious data into the training data of whatever process is training data to create a backdoor which you can exploit during test time. Okay, and then of course there are things like membership interest attacks where you are interested in knowing if a certain sample was used or not in training the model. Okay, but of course we are going to stick to the test time attack because that's the easiest to understand, at least from a theory perspective. So it's an arms race, people proposing new attacks, and other people like providing defense for that, and yeah, it's been going on for a very long time. And last time I checked, this was like the strongest kind of attack, the CW attack, which is what appeared in the talk of Stefan. Okay, something which maybe it might have slipped this far. It's not like there's something wrong with machines. Okay, there's some stuff which is wrong with machines, but part of it is okay. Just the kind of inductive bias you have on your perception might make you fail in very weird ways. So for example, optical illusions, you can think of those as adversarial attacks which are not happening in pixel space, but in some other space of orientation, so this kind of stuff. So humans are not completely safe from this. They have different kind of inductive bias, but it's the stuff. So basically, given time constraints, I'm going to concentrate on only the first two parts of my talk. So I'm going to present negative results for general models. So it's going to be as a result of curse of dimensionality a phenomenon, whereby if you take a set which is not too small in high dimension and you inflate it a bit, it's going to fill the whole space, okay? If you normalize the volume. And then negative results for neural networks, which might be the new highlight if some of you have seen my talks before. Okay, negative results. So this is like one slide to summarize everything. So it's like a law. So the law says the butterfly effect of misclassification. So what are we talking about? If you have a classifier, so basically a classifier, it's any mapping measurable function from some measure space. So think of X as a Polish space, so complete metricizable separable. That's mapping inputs into classes 1, 2 up to K, like think of ImageNet with all the different images. That makes errors on normal. So this is a classifier which is not perfect, say, on the images of cats. It misclassifies some images of cats, okay? The law says under certain constraints, structural constraints on the conditional distribution of cats, these small errors that you make on clean examples are going to transform to a huge disaster when you allow for people to perturb the input. Okay, so this is a law, and you can make this very formal. So what are we to see it? So, okay, in certain spaces, so when I say certain spaces, think of RD on which you put like a Gaussian multivariate distribution with identical variance 1, 1 everywhere, or you could think of uniform distribution of sphere, or any log concave distribution, or even a very more general class of distribution. For example, if you take any like positively curved compact linear manifold and consider the unique invariant measure on it. So for example, in the sphere, it would just be the uniform distribution of the sphere. Then the following happens. So if the blue stuff here is the images of cats, which are misclassified by your model as being like, say, dogs, but these are like normal errors, then you consider this epsilon blow up of this. So you consider the epsilon neighborhood of this set, okay? So saying that your classifier is not perfect on images of cats basically says this stuff has positive volume. Okay, now you inflate it by epsilon and you ask yourself, what's the volume of that outside stuff? Because the volume of the outside stuff is the adversarial error on average that your classifier makes when the attacker is allowed to perturb inputs by a value epsilon. And the whole point is that under certain conditions on the space, the probability space on which this diagram lives, as soon as this has positive volume, this guy is going to grow exponentially in epsilon. Okay, so just for the experts, the property that you need here is you consider a Polish space equipped with a measure, and if that measure satisfies the so-called Lagrange transportation cost inequality, then you're going to have this butterfly effect. Take a small set, blow it up, then it's going to fill the whole space. Basically saying if you are not perfect on normal examples, then you're going to be just so bad when it comes to the adversarial question. Yeah, now of course, if for example, if you argue this using, if you argue on this using the L2 norm and then by equivalence with the square root of dimension factor, if you reduce that to the L infinity norm attacks, you get an exponential dependence on the dimension. Basically, we are saying this is going to go. This stuff is going to fill the space at an exponential speed with respect to the dimension. So you're going to have a class of dimensionality. Okay, so I mean, with all the talks we have seen this far, we already have some intuition of why about these things can happen. So for example, here I'm considering a problem in which there is one strong feature that has information, Then there's a bunch of other features which are like noise. If you do classical machine learning, it's going to say if I average these features, it's going to give me maybe 1 bit of information. But in terms of adversarial considerations, it's a very bad idea. Adversarial, you want to only look at this informative feature. Okay, so in that problem, for example, optimal attack is just to do nothing for this guy because there's so much information that if you do something, the classifier is going to detect. But these people, because there are many of them, you can do a small epsilon perturbation on each of these other weak features, and this is going to change the class level. Okay, so messages, well, I think we can read it together. So adversarial examples are a force of nature. So, okay, we are going to come back to this in a moment. There are certain aspects of adversarial examples which are just due to structural properties of the data. Like if you have two Gaussians which have centers which are very close, it's difficult to separate them. They're always going to be a gray zone. And this is not because your classifier is not good, it's because that's the word. So when I say a force of nature, you should have this analogy in mind. Try to separate two Gaussians that have centers which are close. Okay, there's a certain amount of adversarial vulnerability that not even the best possible robust model can evade. So I mean, you can also use an analogy from information theory. Okay, there's a limit to the rate at which you can transmit information in a noisy channel. There's also a limit to how robust you can be. And yeah, there's certain limits. Of course, the whole point is that you should try your best to scrape this limit, but you shouldn't try to have something which is 100% adversarially robust. It doesn't make any sense. And okay, this stuff resonates with some of the talks. So why do you do, rather than trying random stuff to mitigate robust adversarial vulnerabilities, maybe there are certain interesting other questions like out of distribution generalization, which resonates with the DRO that the previous speaker talked about. And of course, there is interesting. Okay, we prepared this talk not knowing what will be talked about by the other people, but of course there's stuff to be done about verification and also certification. Maybe you don't know, you maybe want to certify that this cannot be an adversarial process, rather than say, hey, I know how to predict it, I know how to predict it, and you predict the wrong level. You can certify and this kind of stuff. Okay, so I'll cross over the second kind of negative results. So negative results for neural networks. So what I said before is general. So the classifier H was just any measurable function, and adversarial examples came about into existence by just structural properties of the space of the features. The classifier had nothing to do with it, except we just require that it should be imperfect. It doesn't matter if it's a random forest, a neural network linear, it doesn't really matter. Now here, let's zoom a bit into things and try to understand other phenomena. And depending on how you look at it, this second part might be connected or disconnected with the first part. So okay, now we all know what's a neural network. To me, a neural network has only one hidden layer. It has all the complexities of what we would see in bigger networks. So input layer, output layer. Input layer has D features. Sorry, input layer, hidden layer, output layer. Input layer has D features. The hidden layer width, so the number of hidden neurons is K, that's the width, that's a very important parameter, and okay, it's just a scalar neural network. So the input dimension, so you could think of this as the number of pixels, for example, the number of hidden neurons and stuff. And okay, so in a neural network, so you would have a bunch of stuff here, you can encode this as a matrix W, so these are the hidden weights, and here you would have one scalar per link here, by which you combine linearly the stuff. And here you have an activation function like a ReLU that Stefan talked about. And these are the learnable parameters. Okay, when you do gradient this here, basically moving over these matrices and moving over this stuff. Okay, so I'm going to consider not general neural networks. Okay, I'm going to consider neural networks in certain regime. So these are the so-called random features regime, in which you only learn V and you force W at the value at initialization. So you could think of the neural network as all of this is random. So you could see this as a random feature map on which you do linear regression. Okay, so you basically do linear regression on a random feature space. And the second case, which is NTK, okay, it will be too technical to talk about it here, but basically you linearize a neural network at its value at initialization, and gives you a certain feature map that you can also do stuff. So all of these things are all about generating random features on which you can do stuff. Now, if you take the width to infinity, this is going to correspond to kernels, and you can consider the associated reproducing kernel Hilbert spaces and do regression in these infinite dimensional spaces. So, okay. So the goal here is to understand the robustness of neural networks, the robustness or non-robustness of neural networks in those two regimes, simplified regimes. Those regimes are simplified so that we can actually prove the stuff. So consider data, so this is a random labels, and this data x1 up to xn are sampled uniformly IID on the units here in d dimensions. And what is important here is that the yi's are not deterministic functions of the xi's. So there is label noise, okay? And we're going to put ourselves in the interpolating regime where we try to learn to learn the labels from the samples. So in the previous talk, incidentally, there was a paragraph about when you're in the interpolating regime with noise, then you might have as example. Actually, you can prove that. And yeah, so one thing which would be important to us is like the error at training, and then the bias optimal generalization error for the problem, okay? And this minus that gives you like the amount of overfitting you are doing. So if this is smaller than the bias optimal generalization error, it means you're learning below, on the training set, you're observing error which is smaller than the best possible you can do, so you're basically overfitting, and the amount of overfitting is this. And the whole point, okay, measure out the robustness of a neuron, of a model by looking at the Sobolev semi-norm. Okay, so you take the L2 gradient with respect to the data of the gradient of the Jacobian. Okay, so this tells you on average how big are gradients. So with all of this, so there's a bunch of laws. The first law is that if you look at the robustness or the non-robustness, so this stuff SF, when it's small, it means you're robust. When it's big, you're not robust. So see this memorization. So you see you overfit your training data. Okay, your robustness is going to be at least this times the square root of the number of points in the training data. So it means that if you have a big data set and you do very well on train, then basically you cannot be robust. There's no way you can interpolate through endpoints and be robust, which is very important. And for the different regimes, you can have very precise results. And that's actually a law, because if you plot the memorization against the robustness, you see it looks like a linear curve. And all of the different points are different experiments, but it's actually a law. So it's linear, and that's also like linear. And different colors correspond to different levels of noise in the labels. And, okay, see. Also, one interesting thing that came out of this is so-called multiple descent in robustness. Has anyone heard about multiple descent generalization? So, okay, it's a phenomenon by which, you know, in classical statistics, if you have too many parameters compared to data, at one point you are going to you are going to overfit. But if you keep increasing the number of parameters, at one point your generation error is going to go again down. So it's this stuff. That's what we call multiple descent. We here observe this in robustness. So basically, if you look at here, so I'm looking at the NTK, and I'm looking at this. Okay, say this is square root of sample size, more or less. So you see it has this kind of linear behavior, and there are certain points at which it goes to infinity. And these points correspond exactly to the interpolation thresholds. So the interpolation thresholds are when the number of samples is equal to either the number of inputs or it's equal to the number of hidden neurons. So these 2 points, they're actually exact, they're analytic. And just for the experts, actually these correspond to like singularities in the trace of a random matrix. So if you take a random covariance matrix, and then you're going to have issues when number of samples, when the matrix becomes square. Okay, so this, but now everything is non-linear. So yeah, and you have the same stuff as that. And then maybe I'm going to end here. So just to again to bounce off to bounce on the last talk. So for example, we can consider 3 regimes. So the question is, adversarial examples, where are they from? It could be from label noise, it could be from lots of stuff. So here, let's try to fit only noise. So here there's only noise, okay? And rho here So in the large dimensional regime in which both the sample size and the input dimension go to infinity proportionately. So the ratio is held at rho. So if rho is big, it means you have more data than dimensions and vice versa. Okay. So when rho is too small, okay, there's nothing. So in this not only case, there's something happening here. So here, the very red stuff corresponds to the log of something which is close to 6, so it's almost infinity. So there's a singularity here where you're very unrobust, because your metric is square. And as you go up or down, it's 0. Now if you look at when you have noise plus signal, so here you have both noise and signal. As you have more data compared to parameters, actually, this stuff becomes big. So the SF, which I said has to be small for you to be robust, actually grows. So in this scenario, the more data you have, the less robust you are in the presence of noise, because your model is going to try to memorize the noise, and it cannot do so in a smooth way because it's noise. And on this, I think I'm going to end, and if one or half question, I could take it. Thanks.
Half a question? Do you think it's possible? We have time for half a question. And you will half answer.
Or one question, no answer.
Hello, thank you for the presentation. It's full of good information. And I know that the Facebook Research Lab is now making a lot of contributions regarding the transformer neural network, which are being applied on images, even though they were planned to be applied on words.
Yeah. It's about ugly, for example.
Yeah.
Okay. Yeah.
So the good thing is that they are applying the attention layers in transformer to detect images or to detect anything else. Now the question is, if an adversarial attack may happen on attention layer, it might make the neural network focus on other things than the one it was planned to focus on. So is the solution that you have provided, not the solution, I mean the results that you have discussed regarding the neural network, can they apply it on attention layers or not?
I see, that's a good question. So the first part applies to everything. So it applies to basically if your classifier is...
You mean the random features?
No, the very first part of the talk in which I was saying, like any classifier, blah, 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 this applies to anything. For the second part, it's a bit more tricky. It's very tricky. So for example, forget about attention layers. Just take neural network in which you learn all the layers. So you see in my neural network, some things were random. If you learn all the layers with greater descent, I don't know what to say. So if you start putting attention on this kind of stuff, it just goes, it's very complex to see actually what's going to happen.
Yes.
Yeah, so it's really difficult actually.
Okay.
Yeah.
Okay. Thank you.
Next question, thanks.
Thank you again. Atem.
Hello everyone. Very happy to participate in this workshop. My talk will be about some tools and methods that have been introduced during the previous years in order to make neural networks more robust. So I will be optimistic. And so the bad news is that I don't have so many images in the presentation. Okay, so just a reminder before we go deeper into the presentation. So the accuracy, we know that it is the fraction of inputs that are correctly classified by so here I'm considering neural network classifier. And there is a notion of robust accuracy, which is a fraction of inputs such that the classifier keeps the same class inside the L2 band centered at the input and with radius epsilon. So our goal is to increase as much as possible the robust accuracy, because the adversarial examples that have been discussed today have shown that we may have neural networks with high accuracy but with very small robust accuracy. So in the state of the art, according to my knowledge, there are three main approaches that have been proposed in order to reach this goal of robustness. So the first one is called adversarial training and has been discussed today. So we pass this slide. The second approach is based on formal methods. So we know that formal methods are very useful in order to validate neural networks, but they can also be used to train neural networks. in such a way to maximize the certified regions at the end. And this approach works well, however, it is not very scalable, but at least comparing with adversarial training, it has theoretical guarantees. So next I'm going to the third approach on which I will spend more time, which is called randomized smoothing. So this idea was introduced nearly 2 years ago. So it is a very simple idea. So we start from a base classifier f, and then we take its smoothing by a Gaussian distribution with covariance sigma square the identity. So it's IID Gaussian samples with the same variance. And we take the expectation. So for each input x, we add so many samples from this Gaussian distribution, and then we take the average decision. And this defines the smoothing classifier. So in practice, what the smoothing does is that it reduces peaks. So like here on the left, we have a classifier which has so many peaks, and these peaks actually lead to the creation of adversarial examples. And by smoothing, we reduce and we limit the effect of these peaks, and we obtain a more classifier with a decision boundary which is more smooth. So the main result is that despite the fact that we smooth with the Gaussian distribution, we end up with a classifier, the smoothed one, which is certified robust into L2 balls with radius r, and so this r here we can explicitly compute it, and so we are sure now that inside the L2 balls with this radius, we are sure that the classifier, the smoothing classifier, is 100% robust and doesn't change the class of the input. So that's the main result regarding randomized smoothing. Then people remarked that we can improve randomized smoothing in the following way. So they remarked that when the input is far away from the decision boundary, we can allow ourselves to take a higher variance, and this gives a rise to a bigger certified band. So they proposed, instead of fixing the variance as we saw before, they proposed to for each input to look for the optimal variance, and this is done by solving the equation. So we optimize the function r of x sigma, so which we discussed before with respect to sigma, and this method showed better results than classical randomized smoothing. Then another approach in which people started smoothing with a Gaussian noise with a general covariance matrix. So now we look for a covariance matrix which is so this is, let's say, more general than fixing a covariance matrix which is diagonal and all the terms on the diagonal are the same. And now they looked for a better covariance matrix, and so first of all they computed the radius when we sampled from Gaussian noise with the covariance sigma here, and then they optimized this covariance function with respect to sigma under the assumption that the covariance matrix is diagonal. And if we assume this, then we reduce the problem to an optimization problem on Rn. So comparing with the classical randomized smoothing, now this approach is able to certify ellipsoids. However, these ellipsoids are either horizontal or vertical, so it means that the axes of the ellipsoids are always parallel to the canonical basis of the space. And it has been shown that these ellipsoids always contain the L2 band that we can certify with the classical randomized smoothing. So next, so before I go to our work. So one limitation of the previous approach is that it is not invariant under rotation, because if I have a data set like this, then I will find a good ellipsoid. However, if I have a data set a little bit rotated, then the ellipsoid that I will get with the previous method is not optimal, because I have this restriction to either take horizontal or vertical ellipsoid. With two colleagues, so Marc Arnaudon, who is the mathematician, geometer, and Paul, who was in internship with us, so we tackled the problem of maximizing the function, which is the radius of the input and the covariance matrix we need to take, and we so proposed the formulation of this problem, which is the following. So first of all, we need to understand where the solution we are looking to, where is the space to which it belongs. So when we look for a covariance, so this is a symmetric, positive, and definite matrix, and this defines a geometric space which is called Riemannian manifold. So Riemannian manifold is a geometric space which is locally Euclidean. And so we were interested in the topology of this space, and fortunately there are a lot of works on this space, because it is involved in many image processing applications. And there is, for instance, a very famous distance called Rauer-Fisher, which originates from information geometry, that is very useful on this space because it has many invariance properties. So there is a framework of Riemann optimization that has been developed on this space, and fortunately we also worked on automatic differentiation on this space recently with so many people, and so we found many tools that are available, and all these tools have allowed us to make optimization on this space and look to the most optimal solution directly using this topology. So now I'm going to the last slide here. So we evaluated, but we didn't yet finish the evaluation. So here are some preliminary results. So we took a neural network and then applied randomized smoothing with the different available methods. So and then we computed for each method, we computed the certified regions, and in order to compare between all these methods, we searched for the radius of the maximal L2 bar that we can put inside the certified region. And what we can remark through this figure is that the Riemannian geometry-based method, it always gives us the highest, let's say, the highest proportion of data that are certifiable inside the L2 bar of the radius that we took at the beginning. I was a little bit quick. I have finished it, so if you have questions.
So we have time for one question. I was wondering whether it has any impact on the sampling process, because you have to choose, at some point you have to choose how many samples you generate, and as you change the shape
yes.
of the
sampling solution.
Yeah, so is there any impact, and do you have ways to, relate the number of samples?
Yes, this is very technical, and it is done with the hypothesis test. There is a hypothesis test, but So when I say 100%, actually it is 99.
Yeah, it's when
Yes.
you have an infinite number of samples.
Yes,
but,
exactly, yes. So,
but you know how to sample even in
yes,
case
yes,
of,
this has been done, yes, yes.
Okay, even
It's
if
a little bit tricky, but
okay.
there is a known number of samples for each dimension.
Okay, thank you. So thank you, Atem. I think we can move to the last presentation.
However, now I have many images and videos.
Other questions?
Okay. So I will quickly speak about the research direction on adversarial robustness in CEA. And okay, my goal was to make you listen to some example of adversarial examples in audio, and especially in speech recognition. Because what we wondered at CEA was, okay, we are working and speaking a lot about adversarial examples, but we were wondering about the practical feasibility of adversarial attacks. Because what we want to consider is that in some domains adversarial attacks are credible, and in some domains it's not so credible. So in this example, we were playing some original file with the music, and usually in adversarial example we are saying that we are targeting imperceptible perturbation of the signal, and unfortunately it's bad. If we listen, yes. Yes, not a problem. Some other examples. If we consider that the perturbation have to be done in the physical world, it means that the perturbation have to be robust. If we have to quantize the signal for a speaker, it has to be robust to some noise in the environment, and also it has to be robust to noise and reverberation. And if we are considering those physical consideration, the noise, the perturbation that we are introducing in the signal is not so imperceptible. It becomes quite perceptible and quite noisy on the signal. So it's not, there are no sounds, so you can see this. So the credibility of an attack on, for example, in such a scenario, for example, we made this demonstration to show that having an adversarial attack in audio means that, for example, if you are considering that, for example, in ways, you have your way on the map, and as usual, Waze is proposing you some alternate routes. You can have some adversarial attacks, for example, from the music you are listening to, and if in the music you are introducing some perturbation, and the perturbation at the perfect time can be introduced, and it says, okay, take alternate routes, and that your car is able to understand this command. So your car can take, autonomous car, of course, I didn't precise this, but your car can take the alternate route. So, of course it's possible, but it's not so easy to make an adversarial attack on this kind of scenario. Of course, in images, we know, and we have a lot of examples in this. And in this video, we try to make a short movie to explain, okay, where does the adversarial example can come from? It's to explain to general audience, but we take the analogy between the neural network and this little game, and we are saying that when we train some neural networks, we are just trying to optimize in this game the position of the wood here. And then when we are doing parameter training, we are setting the position of the of the woods. And then instead of falling in a completely random box at the end, it will fall on the correct box here, based on the initial position in this analogy. In this analogy, what an attack is somehow that you are slightly modifying the first images, and you are exploiting some random, not random, but some chaotic behavior in the fall of the ball. And this, the fact that the neural network is doing some deterministic decision is creating the adversarial examples. And what we've shown in some work with Raphael Pinot, who finished his PhD in 1 year ago, was that when you are considering deterministic decision, you have a way to fool the network. And a good solution to make the network, the neural network, robust to adversarial attacks is to introduce some randomization in the process. And that's why we are considering, as a generic defense, the way to defend against adversarial attacks is to introduce the randomized classifier, which is a generalization of randomized smoothing, and in which we introduce some noise either on the inputs or in the different layers of the neural networks. So in CA we have quite a lot of applications of neural networks, let's say, machine learning in general and neural networks in particular. And for example, we are doing in spectrometry analysis some estimation of concentrations and identification of some components. Right now, we have shown that neural networks are able to outperform historical methods, but it introduces some weaknesses, of course, based on the existence of adversarial examples.
I'm sorry to interrupt you. We need everyone in this room downstairs because it's a conclusion. They've been waiting for you for now 20 minutes. It's a political option, I would say, that's downstairs. It's to show that they can have trust in not AI but us. It's a political person, so please come now. I'm sorry to interrupt you. It's really, really important from a political point of view for the fundings, which is quite important that you can guess. I'm sorry again.
Well, thank you.
Thank you.
And